Good afternoon, everyone. If you may take your seats. I'm Harshvardhan Tripathi, Associate Dean for Research with the College of Agriculture and Environmental Sciences, and John Becker's Professor in Poultry Science. And it's my honor to welcome you all to the 2025 D.W. Brooks Lecture. This lecture and its associated faculty awards honor excellence and encourage innovation and thought that elevates agriculture and environment here at University of Georgia and around the world. We thank you for joining us from near and far. Today, we look forward to what promises to be a thought-provoking lecture, and we continue to carry on the legacy of D.W. Brooks, a man who laid the foundation for the work we do today. The founder of Gold Kist Inc. and Cotton States Mutual Insurance Company, Brooks dedicated his life to the improvement of agriculture, the support of agricultural industry, and the health of our environment. Throughout his life, he advised 7 US presidents on policy and trade issues, and was one of the first inductees into the UGA's Agricultural Hall of Fame, and was named Progressive Farmers Man of the Year in Agriculture in the South. In addition to these honors, D.W. Brooks has the distinction of being both the youngest and the oldest faculty member of our college. He began his teaching career with CAES at 19 years old and ultimately returned to the teaching career after a long and productive career in agriculture. He taught in CAES classrooms until his passing at age 97. We would like to share a video with you about Brooks' life and legacy. Obviously, I need help.
The whole idea in the farmer was that I could bring them all up. And I wanted to get them to where they were the greatest producers and the highest income group. I wanted to take them from the bottom to the top if I could.
He would say, never forget who causes things to happen. The workers in the field who harvest the crops, who plant the crops.
I grew up understanding that farmers were the absolute rock bottom supporters of our culture.
One of the stories that really had a great impact on him was what he would tell about his mother back when he was growing up on the farm in Georgia, here, a cotton farm. And his mother would always said, you don't feed people because they're good or feed them because they're bad. You feed people because they're hungry. He saw the great need for something to happen in agriculture. He was a faculty member at the University of Georgia, and admittedly, I think he left that against the better wishes of the Dean of Agriculture at the university and his own father to try to do something to benefit the farmers of Georgia.
The average money that crossed a farmer's hand in a year was $72. He had been to Denmark early in his life and had seen the co-ops there, and he came back and started what was Cotton Producers, which became Gold Kist.
The purpose of Gold Kist, as Mr. Brooks often articulated it, was to improve the economic well-being of family farmers in the areas it served. Gold Kist was one of the first companies that had poultry servicemen whose total function was to go around from farm to farm and help the producers do a better job at what they were doing.
He was absolutely committed to the fact that profits were to be shared, and that's how it happened in a co-op.
Gold Kist's legacy in Georgia is that many many farm families achieved a much higher standard of living, and their sons and daughters and grandsons and granddaughters continue to enjoy that benefit today through the poultry business. Mr. Brooks influenced agriculture policy very directly. Because Gold Kist was the largest agribusiness in the Southeast, he knew presidents and secretaries of agriculture, secretaries of commerce, other cabinet members.
And he served on boards for many presidents, for 7 presidents.
One of the most compelling speeches I heard President Carter make was at Mr. Brooks's 85th birthday celebration at Gold Kist. He gave him the credit that he deserved for the leadership that he had provided to Gold Kist, to Emory, to the Methodist Church, and to agribusiness in the Southeast.
He loved the university, and that was the only way it was ever referred to in our house. It was the university. When he was in his 90s, he was invited back to give lectures in the School of Agriculture. He loved being able to brag that he had been the youngest professor and now the oldest. One of the things that is so nice about the D.W. Brooks Lecture is that it is an ongoing educational commitment.
I think the importance of the Brooks Lecture today is that it brings the leading thinkers, the leading speakers, the thought leaders to the campus so that young people can see that there are great opportunities in agriculture, agribusiness, agricultural economics, and the environment associated with agricultural activities.
He would be absolutely thrilled about, and he was thrilled about it during his lifetime when he could go. That was one of the highlights of the year.
Today the South is booming, it's doing well, and it's up there even now, and we're doing quite well. So we have great institutions now in the South, and they're training lots of wonderful people, and they're building the South, and that's the way you do it. And so I think the future of the South looks better to me every day.
We are grateful for the opportunity to honor D.W. Brooks' legacy here today and to encourage the pursuit of innovation among our faculty and students. We would like to start by recognizing our 3 D.W. Brooks distinguished professors and take a moment to celebrate their work in honor of Mr. Brooks' legacy. First among them, Dr. Ignacy Mistal, Professor in Animal and Dairy Science. Please stand and be recognized. Let's Dr. Steve Stice, GRA Eminent Scholar in Animal Reproductive Physiology and Director of UGA Regenerative Bioscience Center. I do not believe Dr. Stice is with us today. The third one, Dr. Peggy Ozias-Akins, Professor in the Department of Horticulture and in the Institute of Plant Breeding, Genetics, and Genomics. Now we would like to take a brief moment to introduce to you 2025 winners of our D.W. Brooks Faculty Awards for Excellence, the college's top honor for our faculty. Award winners, please stand when your name is called and remain standing until all winners have been recognized. Audience members, please hold your applause until all have been recognized. The 2025 D.W. Brooks Award for Excellence in Teaching goes to Dr. Laura Elestad, Associate Professor in the Department of Poultry Science, where she also serves as Director of Graduate Studies. The 2025 D.W. Brooks Award for Excellence in Research goes to Dr. Rami Dalul, R. Harold Harrison, Distinguished Professor in the Department of Poultry Science and Interim Assistant Dean for Research at CAES. The 2025 D.W. Brooks Award for Excellence in Extension goes to Dr. Mark Abney, Professor and cooperative extension specialist in the Department of Entomology. The 2025 D.W. Brooks Award for Excellence in Student Success goes to Dr. Woo Kyun Kim, professor in the Department of Poultry Science. The 2025 D.W. Brooks Award for Excellence in Public Service Extension goes to Jeff Cook, Agriculture and Natural Resources Agent and Extension Coordinator in Taylor and Peach counties, and serves as the Area Peach Agent. The 2025 D.W. Brooks Award for Excellence in International Agricultural and Environmental Sciences goes to Dr. Alfredo Martinez Espinoza, professor and UGA Extension Specialist in the Department of Plant Pathology. We are so grateful for your work on behalf of the college. Let's give these outstanding faculty members a round of applause. It is now my honor to introduce to you our guest speaker, Dr. Raj Khosla. Dr. Khosla is the Cashup Davis Family Endowed Dean of the College of Agricultural, Human, and Natural Resource Sciences at Washington State University. He has been involved in precision agriculture since its inception and had made significant contributions to its development and global adoption. Dr. Khosla is the founder and past president of the International Society for Precision Agriculture. His research focuses on harnessing spatial and temporal variability in managed agroecosystems to improve decision-making. His team has used remote sensing and other geospatial data layers to pioneer methods for stratifying productivity zones in crop fields. These efforts aim to improve production, water and nitrogen use efficiency, economic returns, and the sustainability of agricultural systems. Currently, Dr. Khosla is co-leading multi-state, multi-year, federally funded projects to develop and evaluate next-generation sensors and novel AI algorithms designed to enhance water and nitrogen use in irrigated systems. He's a fellow of American Society of Agronomy, the Soil Science Society of America, Soil and Water Conservation Society, and the American Association for the Advancement of Science. He's also an honorary life member or fellow of the International Society of Precision Agriculture. It's a pleasure and honor to be able to host him as our 2025 D.W. Brooks lecture speaker. We are grateful that Dr. Raj Khosla is here with us today to share his talk entitled Cultivating Intelligence, AI's Past, Present, and Future in Precision Agriculture. Please join me in welcoming Dr. Raj Khosla.
Thank you, Harsha, for that very kind introduction. I can't tell you how honored and humbled I am standing in front of you, joining the cadre of leaders and distinguished speakers who have come before me. I'm in awe by the legacy of Dr. Brooks and his contributions across the state. It would not be an exaggeration to say across our nation, as he has advised numerous secretaries of agriculture and president. So thank you, organizers, committee, department chairs, college leadership, and university for extending this invitation for me to be sharing with you some of the things that my team and I have learned and contributed to the discipline of precision agriculture. Thank you. So last year, when I received this invite, we were brainstorming what I should be talking to the audience here. So why not I just take a quick poll of who is in the audience. So how many graduate students? Okay. How many postdocs? Okay. How many undergraduate students? Wow, pretty good number. Okay. And faculty? Okay. Staff members? It's pretty good. Alumni, friends? Okay. All right. Well, thank you so much for prioritizing to be here, to hear the journey of how did we get here? What has been the past and present, and what future may look like? I want you to take a moment and imagine. Imagine how agriculture may look like in 25 years from now. What would be your answer? I know none of us have a crystal ball, because it's hard to imagine the future, right? So why not, instead of looking into the future, we take a moment and look in the past. So here's a picture for you. What is this picture? Anybody? Computer. And it has wheels. It must be a mobile computer. Well, I had the privilege of serving 2 terms on U.S. Presidential Advisory Board for NASA, focusing on positioning, navigation, and timing, or the GPS. And the first time I saw this picture at one of the board meetings, this is the first global positioning systems receiver developed by Rockwell Collins in 1976 that has a 2-seater. And talking to the scientists at NASA, even they could not imagine that in a period of less than 20 years, it will go from the size that will fit maybe 10 or 12 in this room to something that you can hold at the tip of your finger. So when the charge is to talk about future, it's kind of hard. Because as humans, we tend to underestimate our potential. And if you're using a cell phone that you bought after year 2000, you have this chip in it. And the idea for developing GPS, which is the backbone of precision agriculture, was to enable every soldier at harm's way to have positional information that puts them at an advantage compared to our enemies. And you look at this picture, and you look at this picture. This is me in late 90s mapping nitrogen using Minolta SPAD meter, and there was not a data logger, so I'm using RS-232 port and an analog data logger velcroed to my wrist, and then I'm using deep cycle batteries on the tackle box on the back to power the GPS unit, as well as the monochromatic pentablet, which used to be 5 kilos in weight, to power all the systems and walking through and taking nitrogen measurements or correlating it to nitrogen measurements out in the field, and I'll do it for acres and acres to create spatial maps. Looking at the differences in the color for the crop canopy. But let me take you even further back. So what comes to your mind? 1957. Sputnik, you nailed it. The first ever satellite that was put into orbit by Russians. And 8 months later, we put Navstar, the first navigation-enabled satellite put together by US, and that's how it looks like. And the idea was that if we know the almanac of satellite in its orbit, then communicating with the satellite, maybe we can figure out the position on our planet Earth. What happened in 1983? You didn't know this was going to be a quiz. 1983, another landmark event. It was the year when the entire global positioning system came to a fruition. You had enough satellites in the orbit that it can start at providing positioning on planet Earth. Okay? Now, if you were, and I've used this data before, I remember teaching my precision ag classes, and I'll give them older units to my students. And they will go to a benchmark to calculate northing and easting, and you will see a tremendous amount of scatter in the data. And a very common thing is to calculate the circular error probability. It's a two-dimensional data set, X and Y. And if you look at the error rate, is 50 plus meter in each direction. So the best accuracy we have in XY was about 100 meters. And if you look at the publications that were coming out, this is an IEEE publication. It talks about SPS as standard positioning systems. The best we had was 100 plus meters, and on vertical, several hundred. And then there's a protected or precise positioning system that military had access to. And that was a lot better. And of course, as the time improved and you look at the publications that were coming on, the scientists at that time were thinking of how could we incorporate differential signals so that we can go from 100 meters to a more precise system. So I'm going to highlight one name, Dr. Brad Parkinson. Who knows who was Dr. Brad Parkinson? Who is Dr. Brad Parkinson? Dr. Brad Parkinson, father of global positioning system. He wasn't alone, there was a team. In fact, just before pandemic, the team of 4 who were the brainchild behind global positioning systems were honored by Queen Elizabeth with 1 million sterling pound. I had the privilege to work with Dr. Brad Parkinson when I served 4 years on US Presidential Advisory Board for NASA. He's sitting right there, the microphone that is on. And next to him, some of you may recognize Dr. James Schlesinger, the Secretary of Defense, Secretary of Energy, Director of CIA. And I'm sitting at the bottom, center. You can see me a little bit better on the right side. And on the left of me, right there, is Ronald Hatch. Ronald Hatch developed the dual band Courier phase algorithm to go from 100 meters to the thickness of my finger. That was Ron Hatch. He passed away in 2001. So there's a lot of effort, engineers and scientists working together to something we take it for granted. How many of you are using GPS? Come on, everybody should be raising their hand if you're using a cell phone, right? You don't even know it, but there's a lot that has gone before us to enable where we are today. So I'm going to give you a classical Gartner hype cycle. So on the x-axis, you have time, and on the y-axis are the expectations. So whenever there's an introduction of an innovation, it goes through a life cycle. So there's a technology trigger, and the society will say this technology will go do this, do this, do this, do this. And what they're doing in the life cycle of the technology or innovation, it creates inflated expectations. And what happens with inflated expectations? When you cannot meet those expectations, it starts to deflate and it quickly starts to fall down. And as it happens with a lot of technologies, they may not see the daylight in future. But if they survive the tray of disillusionment and sustain the time, then that's where you go through the slope of enlightenment, and hopefully, sustainably, you make it reach the plateau. I'll give you one example. Drones. How many of you remember what happened with drones? It came with a lot of hype. Hey, forget satellite. I can take pictures anytime I want. It will create a lot of jobs, high resolution pictures. You can do it yourself. It'll create lots and lots. And what happened? Within the first couple, 3 years, says, oh, there are regulations. I can just fly over your house, right? We need infrastructure to be able to process those imagery that we can calculating. We need software and we need skilled people. And there's more regulations. And people are thinking that we can commoditize it, we cannot do it. And so what happened in that time period? You lost 3 years of time frame. But as we know it today, drones survived, right? And there's a lot that went behind that, that there was more clarity and ease in regulations that happened. Infrastructure came into play. Other partners starting to come together. Energy, real estate, entertainment, sports. Now, if you look at this curve, this is Gartner Hype Cycle. This is exactly the same pathway that precision agriculture took. It started in sometime in 90s, started sometime in 1980s, and it went through a hype cycle and starts to fall. By year 2000, many were saying this is a fad. It will go away, because at the same time we were having conversation that we need a go-to place. And we need to create a society, what's today called International Society of Precision Agriculture. And if you look at what happened in the last 5 years, it has taken a hockey stick increase. And it's not going anywhere. But something changed in the year 2000. That was a seminal moment. Selective availability, the encryption on the GPS was removed. Bill Clinton signed this into law and removed selective availability. So what happened now? Circular error probable, if you look at the data, it went from plus minus 100 meters to down to a few meters. And in fact, I pulled the data off in this United States Space Command Center, Colorado Springs. You look at the noise on the vertical domain and the horizontal domain, and on May 2nd, 2000, the moment selective availability, which was an induced error, the largest source of error in GPS, it went away. And you look at the scatter at that time. Around the same time, something else happened, which is wide area augmentation system. So this is a group of 6 satellites that were put in geostationary orbit. And that started providing service to all the user of GPS. You don't even know it, but you're using WAS all the time. And so if you look at the summary of what happened, so without removal of SA, you're in the 100-meter proximity. When you remove the selective availability, now it dropped down to 15 meters. You brought in WAS, it puts you in 3 meters. That's why you're never off the road when you're navigating using Google Map or Apple Map. It's a tremendous amount of work that went into that. This is Albert Einstein. And I really like what he said. He said, imagination is more important than knowledge. And I couldn't agree more, because when I look at the history of precision agriculture, what started as a simple idea on a piece of napkin for a group of people like you and I, and that happened to be led by Dr. Pierre Robert, the father of precision agriculture. After a tri-society meetings, Jody, him and his colleagues were sitting, having snacks and beer, and they were saying, what if? What if GPS ever become available for agriculture? And he drew it on a piece of paper, that how we can layer the data sets. And then PPI, and later on, PPI is Potash Phosphate Institute, which later became IPNI, International Plant Nutrition Institute, translated this sketch into a schematic that has been used worldwide, one of the most widely conceptual design of precision agriculture. saying that if GPS becomes available, then all operations on our farm will be connected to GPS. This has happened. But the founders of GPS cautioned us that when farmers and practitioners and scientists will start working on location-enabled agriculture, they will be collecting lots and lots and lots of data, and that's what is depicted here at the bottom half. So when I look into the future, we are sitting on boatloads of data that agriculture is collecting today. So we not only have to train our next generation of practitioners and professionals and scientists and leaders who are engaged in agriculture to know how to farm, but also how to farm the data. It's not only about farming the land, but also farming the data. And this is where data analytics play a very pivotal role. So how do we get there? How do we get there? Could artificial intelligence play a role? So that's the hypothesis. Because if you look at what is intelligence, before we start talking about AI, think about what is intelligence. As humans and several other species, it's our ability to logic, to reason, to collect data and information and integrate knowledge from our past experiences to derive decisions that we may or may not have come across till that point, right? As humans, we learn from early on how to recognize shapes and sort shapes. We learn how to read. We learn how to write. And that's all accumulation of the data and the observations that is happening in our mind, what we call intelligence. We learn how to walk. We learn how to bike. Simple steps, but a lot of data collection and repository in our central processing unit. How to solve problems. And not just solve problems, but solve complex problems. And continue to integrate that knowledge that enables us to continue to think and integrate that knowledge in making better decisions. But we are not unique. We're not unique. There are several species that do that really well. For example, ants, how they navigate in search of food and locating the food and organizing themselves. But there are so many other species, elephants, dogs, pigeons, orangutans, pigs, dolphins, who have demonstrated different levels of intelligence. I don't know how many of you read this paper or watched this video. This was published in Science last year, that scientists observed an orangutan named Rakus in Indonesia who was injured. And so here's the picture from June 23rd, really big, if you can see it under his right eye, really loss of skin right there. And he located a medicinal plant, chewed it, and applied it. You can watch it in the whole video. And by August 25, it was all gone. It's not just the humans, there are other species who are fairly intelligent. But the hypothesis here now, in the world we are living in, is can machines think? And Alan Turing is considered the father of artificial intelligence. And his hypothesis, he created a new domain of computation, that can machines think and can they mimic human behavior? Now, our fascination with machines are not new. Humans were fascinated with machines. We're fascinated with technology and tools, not just machine tools. If you're thirsty, standing next to a river, and you have access to no tools, how would you drink water? We take glass for granted. It's a tool. It's a technological marvel, right? And so our fascination with machinery has been for a while. So fast forward I'll show you some of the technology that is being used in agriculture. These are smart robotic units, and a lot of them are for weed management, because you know that, and I don't need to tell you all, in Georgia, a prominent agricultural state, that farmers have very little tolerance for weeds, for good reasons, because they can take away up to 50% of your production. And so here's the unit that I saw myself in California, carbon robotics. Yes. So they developed the model using 3D machine vision and trained the machine over and over and over again to work on high-value crops such as lettuces, carrots, and they incorporated that in teaching that model that anything other than the object of interest within the planted row, not in between the row, within the planted row, you zap it with a laser. There are no humans involved in the use of this machine. And if you go to California or to some other, and I'm not surprised if it's in Georgia, happening in Georgia as well, you will find these machines that go up and down the farm 24/7 till they run out of energy and they need to be nursed again. And there are several other robotic innovations that are happening, whether working with fruit trees or hauling pots and pans around the nursery, or working with vineyards. I'm coming from the state of Washington, which has 300 commodities. And I was talking to apple growers. They told me that 80% of all expenses in apple production is in harvest. Think about it. So they're really looking for artificial intelligence as well as, and this is also one of our videos, again, from California. Again, 3D vision, but this is mechanical weeding. And farmers are taking advantage of this unit when the plants are young. This is for autonomous sprayer system that can go day or night. Again, no human intervention, for applying fumigants or applying spray, whatever is pertinent for the tree food industry. And that scale of robotic intervention is increasing. The handful that I showed you is coming from 2 years back, International Forum of Robotic Agriculture in California. This is 2-year-old assembly of robotic technology that was available there. In fact, our fascination with technology is not new. This is a 1957 movie from Russia. So here's the farmer and his significant other. And she's saying, look into the future. So again, totally humanless tractors and a swarm of those tractors going across the field. And there are some sensors, and here's a spatial map. And there are sensors out there that can alert the farmer where the problem is. See, he's disturbed now. That's where the problem is, and how he can remotely fix that problem. Well, 2008, Dr. Simon Blackmore, late Dr. Simon Blackmore, he passed away last year. He gave the opening keynote for the International Conference of Precision Agriculture in Denver. And Simon was a great champion of robotics. He was at Harper-Adams University. So if you haven't had a chance to go to Harper-Adams, you're interested in this discipline, I would encourage you to go there to see that. And he was saying in the matter of 5 to 10 years, we'll have swarm robots going through the field. And they did it. In 2017, they made the world record as the first hands-free hectare. So from land preparation all the way to harvest, there was no human intervention in production of this 1 hectare of barley. Now, this was one of the most expensive barley on the planet. but they did it. And Kit Franklin was the lead at that institution. I visited them last year, and they have that program still going on, hands-free hectare. And they're also working on livestock, where there's tremendous amount of robotic innovations that they're developing and infusing into incorporating AI as well. But here's the basic question: can machines think? It's all hinged on that, right? And so a very good example are what? The self-driving cars. We have talked about that. I personally have not come across that, but I've seen videos. Some of you may have interacted or may have driven that. And what does it take to enable that before we translate totally into agriculture? Tremendous amount of sensors and sensing technology. And these are thermal sensors, LiDAR, radar, a dead reckoning sensor that all come together, collecting lots of data around us. So in this example, I rent a lot of cars when I'm on travel, and it'll give you the alert signal that you're too close. Either you're departing the lane or there's someone right next to you, right? It does that. I'm sure you have come across that. And so it's the data engineers who are working behind the scenes to train the AI machine. Your AI output is only going to be as good as the training. Okay? And so what they're doing, they're annotating different objects that the sensors are coming across. And they would label the images. For example, in this image, they're telling what is the car, what is the bicycle, where's the traffic light, where's there's a truck. And they have to do this process over and over and over again. And this is a very time-consuming, torturous process. You cannot just automate this process. Although as the models improve, you can do that. And this is no different than doing it in agriculture. You need very large training data sets in order to have decisions that are false-proof, to be able to recognize and classify objects accurately every time. So here's an example from the tree fruit. We know our faculty are working on counting the tree fruits, recognizing them, and when they're flowering, how they're going to go around and thinning it, not through humans, but through machines, harvesting them, and harvesting at different times of this harvest season, not harvesting all of them together because that's when we had access to the labor. And this is happening in vineyards as well, right now with the high-value crops. I'm going to use a very simple example to train my thought process here, to walk the entire public here. We all use Apple or Google, right, with pictures. So I picked up one of the richest person on the planet, so everybody can recognize that. So you start putting pictures, in this case, Mr. Bill Gates, that this is how Mr. Bill Gates looks like. He wears a dark color sweater and light color shirt, and you start telling the system that this is Mr. Bill Gates. But what happens when he looks a different direction and he wears a different sweater, right? That's a little bit confusing. Right? That's a little bit confusing. So you have to train the computer that, look, this is still Mr. Bill Gates, still Mr. Bill Gates. Well, what happens if he loses the sweater, right? Or what happens if the images start to get younger or older? Will the system still recognize that? Are you still able to accurately? We take this for granted because your cell phone will do it for you. But I'm talking about over 50 or 60 years. How would you make sure that the machine learning and then AI recognizes it accurately? So he's getting younger and younger and younger. And not only just training it to recognize the individual, but also the pattern. And so what happens if he all of a sudden is very young and you ask the machine, what comes next? And what happens if there are anomalies, right? So who is this person? Steve Jobs. That's exactly right. And so it turns out that Steve Jobs and Bill Gates didn't look too far apart in that time frame. And what happens all of a sudden if you insert another anomaly? And look at the distinction over 50 years. That this is a much older recent picture of Bill Gates. Now that's an overly simplistic example, but there was a reason for that because I'm a soil scientist. I work with soils. Now do the same thing with soils. It gets very hard. And I'm not just interested in recognizing the soil color, I'm interested in characterizing chemical and physical properties of soil using sensors, training the data, and developing an AI for us to be able to do that. My postdoc did tremendous amount of work using fluorosensing on 12 channels, and we published a paper where he was mapping chemical properties using machine learning and AI. This was published in the Sensor Journal. And so there's tremendous amount of applications of AI in agriculture, and many of them are in nascent phases. Some of them might be available, from yield predictability to monitoring. A lot of them are focused on monitoring today or diagnosing, so that we can someday help translate into meaningful decisions. But I want to caution those who are very excited about AI, because AI lacks common sense. What do I mean by that? You tell the AI the birds fly. Well, what happens with penguins? Right? So you have to train. But tell me, how many of you have seen a bird drenched in very thick oil? Anybody? A couple of people? 3 people? Can a bird drenched in thick oil fly? How do you know that? Think about it. Does AI has that? So AI lacks that common sense. But then I turn around and say, a bird, wet bird, can a wet bird fly? What would be your answer now? A lot of people are nodding yes, because a wet bird, what that bird is going to do exactly that. So how do we make sure that AI, so relying on AI, you have to be very careful, because it depends on the training data set. And agriculture data is very organized, right? No. First of all, we lack that data, and 2, it's highly fragmented. So organizing that data set, which is near and dear to, and that data privacy is also an issue in this domain. We have to be careful. There's another, you can read it for yourself. This is an old news. You can fool AI. So this was a person on a busy, on an empty, vacant road. He's walking in a cart with 99 old phones, all turned on. He's just walking leisurely. Now, Google is collecting active data, and it's forcing the entire traffic to go somewhere else, because that traffic is totally jammed, because you're getting 99 data points. So AI is not smart. As humans, you will know better, right? And there's another report that came out that ER doctors are not relying on AI anytime soon. I mean, that kind of makes you nervous too, right? Because if you look at false positives, do you have that room for error? You don't. Let me switch gears here. USD Agriculture Innovation Agenda that came out in 2020. I was part of the system design thinking. There was a National Academy of Sciences report, Science Breakthroughs 2030. I'm a co-author on that, and that became the brainchild of USD Agriculture Innovation Agenda. So for those who may have read this, it calls for that by 2050, US is going to increase our food production by 40%. Do you think we can get there? Come on, there's so many pessimists. We can increase food production by 40%. Thank you for nodding. Yes, we can. I mean, if you look at the last 60 years, we have been increasing our food production by 1.43% per year. One of the very few countries on our planet who have created this track record. So increasing our food production by 40%, yes. But you'll say, hey, there must be a catch. And yes, there is a catch. That will do so by 50% less water and use of agri-chemicals. I want you to think about that. How would we get there? Compared to 2020 levels, how would we get there? So this is where I really think precision agriculture has a major role, because just to give you an idea of the magnitude, let's look at how, and I worked with corn or maize, how corn yield looked like in 1900 and what we're talking today. So area needed to grow 28 bushel, which was our national average in 1900s. National average for corn yield, about 2 tons, 1.7 tons in 1900. So the area needed to grow that much corn was 1 hectare. By 1950, we reduced it by 25%. Increase yield 35% in the 50 years. Okay, so the area needed was 25% less, right? But then hybridization happened in corn, a lot of technology, integrated pest management, new varieties, production practices, nitrogen use efficiency, dramatic change in those 50 years. We went from increasing 35% in the previous 50 years to increasing 360% in the next 50 years. What's the national average today? 177 bushels or 11 tons per hectare, right? And so that we have improved another 30%. So if you look at USD Agriculture Innovation Agenda, for us to increase our food production, or in this case, maize, by 40%, we're talking about reducing compared to 1900s, that what it took in 1900, 100 units is going to take only 8 units. There is intensification of agriculture. There's no question about it. Okay, so this is where precision agriculture, the 5 R's, the right input at the right time, place, amount, and manner, plays a very big role. And how would we get there? Well, if you're going to rely on AI, we have to learn how to manage. And we can only manage what we can measure. And for measuring, we have to come up with sensors. Okay, so we are at the cusp of revolution in sensors and sensing technology. We not only need sensors, but we need sensors that are rapid, they're reliable, they're reproducible, they're non-destructive. You're not taking samples away from the field, non-destructive, so that you're going to put sensors that are in situ in the soil or in planta, on the plant, sensors that are variable. How many of you know of eye diapers or smart diapers? There are sensors in the diapers. When there's a change in humidity, it sends you a signal on your app saying it's time to change the diaper for the child. And so we're talking about sensors that are small, destructive, non-destructive, so you can create an internet of soil or internet of plants. And sensors that are degradable. You don't have to go back and collect them. And guess what? They're cheap. They're cheap. That's how you can put them in a diaper. No batteries. Passive. And not only that they are reacting to a symptom, they're picking up asymptomatic detection. Asymptomatic, before a symptom appeared to our naked eye. And you're not going to put one sensor on a farm field. You're going to distribute them in high spatial densities in a field. And that's a tall order. And if you don't believe me, this is coming directly from the National Academy of Sciences Science Breakthroughs 2030 report. And my lab and I, along with Berkeley and UC Boulder and others, and many, many other labs, have been working in this space. I'll show you some of the things that we have been trying to do. So these are some of the domains in sensors and sensing technology that they mimic human sensors, right? And one of the ones that have been used most are the optical and the radiometric sensors. But it's dramatically changing. The field is dramatically growing and changing, right? So we're mimicking human sensing. early and asymptomatic stress detection. So this study is coming from Israel. Okay. How many of you believe that plants cry for help? There are some hands going up. Okay. So that was the hypothesis they have, and they worked with multiple plant species and embedded acoustic sensors to pick up the signals for 3 different stressors. Okay, so the stressors that they used was radiative, okay, water stress, physical stress, and radiation stress. Now, in the natural world, these stresses do not happen in isolation. So they collected data in isolation, okay, in chambers, and then they commingled the data together. And of course, then they used CNN, or classification technique neural networks, to be able to commingle it, and they nailed it. You hear those signals? Okay, my voice was louder, sorry. And what's happening is that depending on the nature of the stressor, plants, there's a bursting in cells that is happening. And depending on the nature of stressor, that signal is unique for each of them. And they commingled it and they nailed it accurately every time, using first training the model and then using AI. This is an example coming from nearby state, North Carolina State University, where colleagues are working on implanta sensor that you can just put it like a Band-Aid on your arm, or in this case, plant. And what they're trying to study is they're looking at the volatile compounds. So whenever a plant is under stress, it releases volatile compounds, right? And so they're trying to discern, they're inoculating the plant or infesting the plants with different inoculums or infestation to look at those signals. And of course, they're able to do this 4 or 5 days in advance before a symptom appears that could be picked up by naked eye. How about that? Okay. And what kind of sensors are these? These are printed sensors. And so when the first time a group of engineers come and contacted me that you're interested, we want to work with you on sensing, and we can create sensors for you. I said, wow, that's an aha moment. They said, we can print the sensors for you. So I didn't believe it. I went to their lab and I saw their graduate student printing the conductive, using conductive, and just literally printing the sensor formation right there. And so we have gone through, this was funded through ARPA-E. We wanted to create a passive, no battery, totally degradable soil moisture and soil nitrate sensor. We went through a lot of testing phases, looking at a lot of different materials, and provided accelerated degradation. Imagine in soil, you have soil pH going on, you have microbial properties going on, you have so many different factors that can influence, and then a whole generation of greenhouse studies looking at what degradation may look like or how quickly these sensors may fail, okay? And of course, sensors fail pretty rapidly, and these are some of the published work that came out of that lab. I'm going to just share with you really quickly. This is very simple. So we select a biodegradable material, then we use a stencil to etch that surface, and then we filled it with the conductive ink. A lot of time it's silver, zinc, or gold, but don't worry about stealing the sensor. The sensor may cost you less than $1, okay? So the sensor is not where the money is. We etch the surface so that it can conduct electricity. Then we connect the 2 wires. In this case, this is a soil moisture sensor, okay? And then we encapsulate it, and then encapsulation is also very important. We had to try so many different types of encapsulation substrates to make that happen, right? I'll show you, and this is a mold. I'll show you my colleague.
Also with substrate
Right.
that we print on.
Right.
So we put a stencil on top
Right.
in the shape of the electrode pattern.
Right.
Right. And then we use just a blade to coat through this stencil pattern.
And the ink is right
Then
here.
we use an ink like this.
Yep.
Yeah, exactly. We use a zinc ink.
And when you do that,
And when we do that, we get a we get an electrode pattern that prints on the balsa wood that looks like
Correct.
that, made of the zinc.
Correct.
But it's not conductive, so we
Correct.
have to make it conductive. So we dip it
Yes.
into a solution of acetic acid,
Correct.
which etches the zinc oxide layer
Correct.
and makes it conductive. Then we attach wires
To be able
using
to communicate.
to be able to communicate with it, to interact with it. We use a, like an epoxy to do that. We
Yep.
connect the wires.
And you use this mold.
And then we use a mold, and in the mold, we then coat the wax. We have to be very careful. Like, a lot of the trick in this is coating the wax and making sure there's no cracks.
Gotcha.
Right? The wax, like you can
Got
see,
it.
it's a very good wax coating.
Correct.
And so that's trick, and that is basically a complete sensor,
And
right?
if I go closer, I will see the communication wires
You
right
can see
there.
the wires, yeah. So
Right.
we can connect these obviously to electronics,
Okay.
and then ultimately in the future we'll just connect them to a
So,
RFID.
so
chip.
the first prototype may look something like this.
Like this, yeah.
Miss-
and so
it's missing the board right
it's
now.
missing the electronics board, which will go there. So there'll be an electronics board here, which will do Wi-Fi communication.
Mm-hmm. Okay.
These two wires.
So our university Office of Research did a cover story on that, soil sensing for field testing. And actually, so as we come up with several generations of these sensors, we will test them against the wired ones, because these are totally wireless sensors in the greenhouse before we go to the field. And we will grow plant to make sure how their performance is. 2 years back, we created a Internet of Soil Moisture on our North Farm at my previous institution, where we put sensors at 2 different depths. So in a very small area, size of the stage right here, we embedded 24 sensors in the field, and this is that field. We learned lots of things. Communication can become a problem when the sensors are in the soil, so we had to put another repeater. And then you can have an API that you can develop. This was a commercial sensor that we're working with company out of Finland that provided us some prototypes for us to work on that. And depending on how frequently I am actuating the sensors from our lab, it instantly creates a soil moisture surface. So I want you to think about it. You have X and Y, okay, and Z, depth. And depending on how frequently you're actuating it, you have time T. With me, right? And so every time we will actuate the sensor, you will have T1, T2, T3, T4. It will just collecting the data and collect numerous. We have so many questions to this kind of data set that we can't answer today. At what frequency should we be collecting soil moisture data? How many depths do we need to calculate? Plants go from very small size of a seed to a very long with deep rooting system. How do we integrate data sets from the depth? How should they contribute? What should be the weight matrix in terms of contribution of moisture coming from the lower depths versus the top depth? And how do we integrate that into decision model? And so this is a study site funded by the USDA NIFA project. This is in Fruita, Colorado, where this is in action. We go out and collect numerous data layers about soils. This is destructive sampling, of course. Electrical conductivity mapping, that creates more data layer. Soil moisture, again, the sensors that I showed you. Imagery through drone and satellite imagery. And of course, a lot of crop biophysical parameters that students would measure throughout the season. And at the end of the season is grain yield map. And this project is enabling, and Dr. George Velitas is part of the project because he has done and his team has done a lot of leadership in variable rate irrigation management systems. And so our hope is that, and this is a real location of the sensors in that field. At the bottom, the line that you see is the linear irrigation system that has nozzle level ability to change the application of water in X and Y and the linear. So our idea is that we upload a prescription map, but then the sensor interact with the linear and changes the rate of water application on the fly, because it takes 2.5 days. So depending on the size of the field, it may take 5 days for circle to go across the field or the lateral to go across the system. We're not there yet. We have tried it. in numerous ways, so significant progress is being made. Looking into the future, imagine you're a professional or a farmer, and just using a ChatGPT as an example, and you're interacting with AI, right? This doesn't exist today, just so you know, caution. So you're saying, hey, when should I irrigate the field? You just ask that as a question, and the AI immediately responds, hi, Carl, let me ping the soil moisture sensor, fork the satellites, and see where we are. And said, depending on how much it had rained, you may need only 2/10 of an irrigation. You can water in a couple of days. So then Carl says, how much water should I apply? Right? That's the normal question. So again, AI says, well, okay, 1 inch would be sufficient. Carl says, I need a prescription map. Of course, it's AI. It will generate it right away at the prescription map. But imagine having the AI that you're interacting with AI, it'll start making suggestions, right? So it says, go ahead and upload it. He said, well, looking at the data that's coming from the nitrogen sensors, it seems like your crop will benefit from nitrogen application. And Carl says, no, I don't think so. He said, well, remember that north part of the field took a 20 bushel yield hit last year. You still do not want to apply nitrogen? He said, no, no, okay, go ahead and apply nitrogen because I don't want to take that kind of hit. Set a reminder. We're not there yet, but we're hoping we get there at that point. But lots of team members, including graduate students here and many other laboratories that are working on infusing AI into making decision-making systems. Our lab has focused more on nitrogen and water. Thank you again for your attention.
Thank you very much, Raj. We'll now take questions from the audience. For those of you viewing remotely, please type your question into the Q&A box. We will read your question out loud for the speaker in Athens. Those of you here in Athens, please stand and wait for the microphone. One of our student ambassadors will bring that to you. And when you ask the question, please state your name and affiliation, and we'll go from there.
So I enjoyed that greatly. Thank you. And I'm Bob Kimmerite. I'm an extension specialist. And so my career is built around building relationships and trust with farmers. And so with the exception of the second to last slide, I didn't see a single farmer in any of your slides. So my question for you is, in your vision for the future of agriculture, is what I do, building trust, building relationships with men and women who are farmers, is that going to be quaint and a thing of the past? Or will farmers and what they do still have a place in your vision for what agriculture will become?
Yeah, that's a very good question. I started my career in Colorado State University as an extension specialist, developing precision agriculture program when in the state we didn't even have 100 acres in precision agriculture. And you're exactly right. Building a relationship is one of the key things that we do, and we do so well at land-grant institutions. So thank you for what you do out in the field. We will never eliminate farmer. We will not. We will be working as this tool in the near forcible region time frame. We'll be empowering the professionals and practitioners to help them make better decisions. But the actuation of what happens in the field would still be driven by the farmers. So we may embrace AI to help us make better decision-making, because imagine a farmer, and there are farmers that are willing to embrace this kind of technology and are willing to take the risk on one field or a portion of their field. They're very cautious about that. Because for you and I, it's publishing more papers. For them, it's their life and livelihoods. So we need to appreciate that. And absolutely, that relationship and trust building has to be there. Right now, you cannot rely. And that was part of my couple of slides in there cautioning that you can't just blindly rely on AI. I've started using generative AI just recently. I've asked some critical questions, and they give totally absurd answers. totally absurd. And they will give references, then you go click on those references, they were meaningless. So yes, that relationship and trust building will still be there. Yeah, 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 back there.
We have an online question here, and that is, how can small scale home growers use this technology? Any research in that area?
Yeah, that's a very good question. I'm asked this question many places, particularly in developing and emerging economies. And there's a very large wave, if you may, where people are working on frugal innovation. And that was also part of our intent, that these sensors, when you print them in hundreds and thousands, our estimated cost may be a few pennies or $1. So the money is not in the sensors. The money is in the data, because you need infrastructure to be able to harness that data, collect that data, develop the training model and the algorithm to translate that into decision-making process. In many of the emerging economies, what they're doing is the private companies are investing into sensor fusion network, where they're putting a cluster of sensor and their stations in different fields, which are small enough. It's just like what Trimble did many years back. They started putting towers on grain elevators. They teamed up with cell phone tower companies, and that provides them static GPS information that they can broadcast the vector data or the correctional data that gives you a more precise positioning, right? And so some of the models that I have come across in consultation with emerging economy scientists and professionals is teaming up with corporations or private partners who are working in this space. They're service providers. So farmers are not purchasing sensors. They're not purchasing data. They're not struggling with that or challenged by that. These are the service providers who provide them when to plant, when to apply water, how much water to apply, what kind of variety to grow, just whole package of practices. So frugal innovation is going to be and is a very important component of particularly AI and other progress that we're seeing happening in agriculture.
My name is Vignesh. I'm from postdoc. My question is, during the summer, how the sensor brings the chemical from the soil? For example, nitrate sensor deploying in the field, how the sensor bringing from different location nitrate placement in the soil?
Yeah, this is something that we also have struggled with, that how are we going to disperse the sensors, right? And how we're going to place them. We came up with different kind of gadgets that one of the first ideas we had that if the sensors are small enough, we can put them along with the bag of seed. So they're thrown during the planting, but then you're putting those sensors with those seeds in a very linear format, right? And will they get distributed? There are other ways that maybe we can use drone to just put them on the surface. What we have done so far in our test, we physically go out and put the sensors in the field. We've also have a part of the project, an advisory board of farmers. How would they like to see installation of these sensors? When they compare the existing technology, which is expensive, bulky, time-consuming, labor-intensive to organize the sensors, versus what we are projecting, if this ever get commercialized, which I sure hope it will, very different outlook. So we have not yet overcome the dispersion of sensors and how many would we need in a particular field. How often do we need to collect data? At what depths do we need to install? There are several other challenges that are prior to that and are more pressing before we start addressing that. It wouldn't surprise me. We're thinking, okay, what if we create a sensor in the shape of a golf tee? So you go there, drop it, and just push it with your hand, push it with your feet, if you're only calculating surface, right? But how do we get to the surface, subsurface one? Maybe taking a push auger, dropping that in, filling that soil, and then dropping another one. So no, I would be open to ideas and how we should be dispersing sensors. Thank you.
The amount of water that is used in data processing, these big data processing centers, is tremendous.
Yeah.
So I'm wondering, in a future that is focused on precision and lowering the inputs of finite resources, how is water taken into account in this?
Water or power?
Water. The water consumption that's used for cooling these data
Oh.
processing centers.
Yeah, yeah. No, that's a good question. I have not given thought about that. I do know that as we continue to enhance nitrogen use efficiency, so the biggest consumption of energy in agriculture is what? It's outside of farm, but it's nitrogen. Nitrogen, to produce nitrogen right now, the way we produce nitrogen, it takes energy consumption global worldwide anywhere from 1 to 3%. Global energy and production of nitrogen. So if we continue to improve nitrogen, not only it will help for the environment, but it'll reduce our energy consumption. So that's one direct, it doesn't directly addresses what you're saying. I know that Coca-Cola was working on their sustainability goal, just like other organizations are. They want to be net zero. Net zero means energy neutral, carbon neutral, and water neutral. And this particular organization, they had a goal for 2020 where they wanted to consume 1 liter of water to producing 1 liter of product, which is close to impossible. But I know in Stockholm at the Global Water Conference, they made an announcement that they have attained their goal by 2019. And the way they have done is partnering with farmers and farming communities worldwide and infusing technology which cut down the water application without impairing the output. So I would imagine there will be novel models coming that reduces the water footprint. And if we do achieve the USD Agriculture Innovation Agenda to reduce our water footprint by 50%, and if we don't change that, unfortunately, for example, the largest freshwater aquifer, Ogallala, is receding significantly right now. And in droughty years, it recedes even faster, 20, 30, 40 inches a year, which is unsustainable. So infusion of some of these technologies and so many other methodologies like more drought-resistant crop varieties, that reduces water consumption as well. So yes, this is a finite resource, how we consume it, whether for data centers, cooling those, or for reducing it in our crop production. Right now, agriculture is the largest consumer of water on the planet. Yeah.
Question here. Do you think precision agriculture alone will allow the 40% increase in productivity in the United States, or will other factors like behavioral and cultural changes be necessary?
Oh, yeah. So the answer is right in the question right there. No, I was at no point of time I was suggesting that precision agriculture is by itself is going to increase the production by 40% come 2050. Absolutely not. We have to work hand in glove with so many other changes that have and Extension has a very major role to do that. Not all farmers are identical. Not all of them are practicing precision agriculture, and it's okay if they don't practice precision agriculture. We have to look at a sum total of options, tools, practices, technologies that are available for our farmers and farming community to embrace what works in that environment. And that's why in one of my papers, I mentioned for this to work, for technology to work, it has to be site specific. What works in Georgia is not going to work in Washington. It has to be site specific. It has to be operationally feasible. If you're a wheat farmer and you're giving options for corn or some other crop, it's not going to work. It has to be economically affordable. You can come up with the best solution for sustainability or protecting the environment, but it does not hit the bottom line. Farmers are not going to embrace it unless it adds value to them. So site-specific, operationally feasible, economically affordable, and locally adaptive. We can come with a value that adds value in certain environment, but doesn't fit into what our farmers or growers are doing. If it's not locally adaptive, it's not going to happen. So there are so many other factors that have to happen for it to make a difference. Yeah.
Good afternoon, Raj. First of all, thank you for accepting our invitation, and thank you for the stimulating presentation. I have a question to ask you about sensors. You may remember that in 2006, The Economist magazine had a cover that said smart dust, and it had a picture of a farmer sowing sensors. The point was they were going to be so cheap, biodegradable, as you mentioned. That was 20 years ago. And I have great optimism, just like you, that we are on the cusp of having that breakthrough. Do you think there's been a seminal moment like the removal of selective availability that has made sensors or will make sensors be the smart dust of the future?
Yeah, that's a great question, George, and thank you for reminding me of the article that hit the cover page of Economist magazine. You are right. We need a lot more investment in agriculture discipline than we are getting right now, or for the last 30 years. Our infusion of dollars in publicly funded research has been on a slippery slope. So that has to change. Two, there are advances that are happening in other nations. For example, there's an article that came out just recently. Japan has released bees, these robotic bees that are size of the tip of my finger, that pollinate flowers, because there's a reduction in the bees population. And they're doing that, and they can do it successfully. You think, wow, that's a marvel, but at the same time, you think, wow, which direction are we moving as a society? Why are we losing bee? And I know several entomology programs around our nation are really stepping up and working on pollination aspects and bees, and how can we really reverse that trajectory. With the USDA innovation agenda, if we do get to a point where we reduce agricultural chemicals by 50%, all of that would help towards the bee. Coming back to your question on the sensor sensing technology, we have a lot of work cut out for us. And it's not just the role of soil scientists or precision agronomists, but we have to work across discipline with people in medicine, people in engineering, people in sociology, people in humanities, all come together to address this wicked challenge of producing food that's healthy, safe, environmental friendly, and leaves a sustainable environment. And sensor is going to be part of that equation in our development process. But that needs a lot of like-minded people coming together. How many years will it really take for the sensor dust may happen? At the National Academy of Sciences deliberations, I've heard there are nano sensors, and I know there's a group of colleagues that are working at K-State, at least I know, on nanomaterials that will later become either nitrogen sensor or phosphorus sensor. In fact, they just got NSF funding to create a global biosensing centers. So there are efforts that are happening that will take us in that direction. What kind of timeline would it be? And you're right, it's 19 years since that article. We're not there yet. And just proving a concept like what we did in our experimentation, but translating that into a commercial viable product, that's another life cycle right there. So yes, I'm an optimist. I would like to see that happen sooner than it can, but obviously there are so many challenges in our journey before we get there.
Okay. Yeah, Ramana Piripadi from the College of Engineering. Very interesting talk and inspiring. I think my question is related to the education part. So we want to train the next generation students and engineers. So what kind of competencies do you think we need to be taught for the students so that they can contribute to these modern technologies?
Okay, so I'm getting a very strong echo. If I picked up the question correctly, what are the opportunities for students, right?
And also the competencies you would like to teach them so that they can make contributions.
So there's a report that came out last year, Governmental Accountability Office, GAO, and I and several others around the nation worked on that report. What's holding precision agriculture back? That report is available in the public domain. Please download and take a look at the report. There's a whole listing. So it gives a full scale of adoption across our nation. So Georgia, the data is in there. Can take a look at it. It goes from 20% to some elements of precision agriculture to 80-some percent, because just the diversity of what people have embraced. It talks about what it will take for us to continue on this pathway for enhancement of education and extension. Availability of skilled labor, people who understand to be able to answer. Agriculture machinery is getting more and more and more complex. When farmers have questions, where do they ask the answer? Extension has a very critical role to play. How many of our people who are getting trained in this area are going into extension? A lot of time they're being absorbed by private companies. What role or ease AI will play, and how our next generation of leaders, and particularly students, would be workforce ready, that they have an understanding of AI. It has a whole listing of ideas and changes in policy that must happen if we really want to have a significant growth in the adoption of precision agriculture. But extension, education, infrastructure, skilled labor, curriculum availability, not in just sporadic areas, but just, a very wide curriculum to prepare our students who are in agriculture. Doesn't matter whether you do precision agriculture or not, it's just part of the curriculum. Because whether you are precision agriculture or not, if you're buying a new sprayer, that technology comes with it.
Please don't leave yet, Raj. Thank you again for being here. And please accept this.
Oh, wow.
No, it may be.
He's taking a picture.
Maybe.
Okay. All right. Okay. Thank you. Thank you. Wow.
This is always a special day for CAES, a day where we take a step back to reflect on all the excellent work that we do, and to gain inspiration from our guest speaker for ongoing and future initiatives. Congratulations to our D.W. Brooks Award winners, and thanks to each and every one of you for joining us today. Thank you very much.